Okay, guys, let's get started with energy and energy conservation. This is the first kind of introductory lesson that we need to cover to start talking about energy. Um, by the way, I know the audio sucks. I'm recording on my headphones and realize it's a bad idea. I'm going to try something else out for the next video, so just bear with me for now and we'll see if we can make it better. But moving along, what we're going to try to discuss today is first energy and energy types. So energy is kind of a category, and one of the things we'll be concerned about is trying to essentially build like a taxonomy. Um, if you're not familiar with that word, it's kind of like a way that we group and categorize energy. It may be worth giving that word a Google. So if you want to pause and go Google that, might be a good idea. But we're going to try and basically build a system to understand all the different types of energy and where they fit in. And then we're going to look at some energy equations so that we can start to calculate energy and put some numbers to it. And then last, I'll do some examples of both identification and calculation. The things I'd like for you to be able to do when you leave here is to, number one, be able to identify different types of energy. So we're going to talk about 3 different types that you really need to be able to identify. And I want you to be able to look at a situation and tell, okay, these are the types that are going on. The second thing, so that's identify. The second thing is to calculate energy that's present. So once you've identified what's there, I want you to be able to actually like put numbers to and solve what's going on there. And the last thing is we're going to just kind of start to introduce energy conservation. We won't focus on that, but it'll be kind of something in the background. And you should be familiar with that from other classes, but we'll touch on it. So getting into energy and energy types. The first thing is that there are kind of broad categories, and here in a moment off to the side, I'll start to build our little taxonomy here. But the first thing I want you to know is what energy is. So energy is a scalar quantity that describes the motion or potential for motion of a body or a system. Now, the first thing that's really important there is the scalar. So you should remember that a scalar quantity is going to be a quantity that it only has a magnitude. So when we talk about energy, it doesn't have a direction. So we'll talk about later that energy can kind of be positive or negative. In this class, it's mainly positive. More on that later. But so energy is a scalar. It doesn't have a direction. It's not forward, backwards, left, right, up, or down. It's just you have energy or you don't. And that's really useful because that means that energy will always kind of add together. And the other thing I want you to clue in here is that it has to do with motion or the potential for motion. So when we're talking about energy, it's kind of like a system for us to keep track of motion in a system. So sometimes the analogy that I'll use for energy is it's kind of like the currency of motion. So you have to have money to be moving, and to get something to start moving, you've got to give it money, if that makes any sense. And we'll dive more into that as we go. And the last thing I want you to clue in on is this idea of a body and a system. Especially for AP, we're really concerned with the idea of what's going on with a system. And so we're going to be very careful to try and think about how we're defining our system and what goes into that and what doesn't. So real quick, I'm going to step off to the side here and start building our taxonomy. So up at the top, we've got big energy. That's the big first topic. We've got energy. Now underneath that, we're going to break it into 2 categories. One is mechanical energy. And that's energy that's readily usable for motion. So basically the idea there should be that either an object is moving, and that's mechanical energy, or it could easily start moving. And that'll make more sense when we talk about potential energy here in a moment. And the other one is non-mechanical energy, which is energy it's not readily usable for motion. Like if we're going to take that energy and use it to make something move, something complicated is going to have to happen. So underneath here, we're going to have 2 categories. Non-mechanical, so that's the first one, and mechanical. So these are the first 2 broad categories that we use. So energy is breaking down into those 2. So diving into mechanical energy, we're going to further categorize two general things. So kinetic energy is something that is moving, right? So it's energy present in a moving object. Anything that's moving has kinetic energy. Potential energy is going to be energy stored in a system, and key word here, system. We'll talk more about that later on, but potential energy is going to require sometimes multiple objects to be involved. But it's due to a relative position. So there are two types you'll need to see here of potential energy. And actually, before we go into that, let me go to our little taxonomy here. Mechanical energy gets broken down into two categories, kinetic, so that's the first one, and potential. So kinetic is, it is moving. Potential is, it could move really easily. And so when we look at gravitational and elastic here, I think you get a sense of why that is. So imagine, I'm holding a ball, right? And it's some distance off the ground. Well, if I'm holding it, all I have to do is essentially stop holding it, and that ball is going to fall, right? So we could say it has the potential for motion. It doesn't require a complex process to get it moving. It just requires that I get out of its way. So that is gravitational potential energy. That's one example. Here's another one. Let's say that I have a spring, and I press a block up against that spring. Well, again, if I just stop holding the block back, the block will start moving. And so that's another example of energy that's stored and can easily be released. So that's how we define potential energy. It's energy that's stored and can easily be released, no need of a complex system. On this note of the system here, if you think about this ball dropping scenario over here, you can see why a system is necessary, because the ball requires something else to have that energy. Namely, it requires the Earth, right? So the Earth has got to be there exerting a gravitational force on the ball to get it to fall. So when we look at potential energy, that often requires multiple things to be involved. And when we're talking about potential energy, we want to make sure that we're acknowledging that that's a property not of the ball. Okay, it's not that the ball has potential energy. It's that the ball Earth system has potential energy. And that may seem like a minor nitpick. It'll be really important when we get to work later on for you to understand that difference. So before we move on, I'm going to go ahead and go separate out that we've got gravitational and elastic as both types of potential energy. So I'll go back over to our little flow chart or a little taxonomy here, and I'll break that down. So I've got elastic and I've got gravitational. So I've got two things under there. So maybe I'm drawing it a little sideways. It's a little funky here, but maybe you can see kind of how the taxonomy breaks down. So you've got energy up top, right? So energy is the big thing. And then that's broken down into two categories: non-mechanical, which we'll talk about in a minute, and then mechanical, which is basically anything that's readily usable for motion. And then we break that down into kinetic and potential. So kinetic, again, is it is moving. And potential, you kind of think of it as like it could move, right? And then you've got two reasons for that. Maybe something is deformed, that's elastic potential energy, or maybe something is at a relative height, like it could fall, and that's gravitational. So that is the taxonomy that we're trying to build there. Okay, going back over to our notes then. So mechanical energy, non-mechanical energy is that other category. Now, non-mechanical energy is we kind of treat it as like a bucket that we want to throw mechanical energy into as it kind of gets converted, and we'll talk more about that when we get to work. The important part here is that you understand that it can be transformed into mechanical, but only through a complex system. So the word there, complex, is really important. And if you look at the examples I've given down here, I think that will kind of make sense. So you've got thermal, chemical, nuclear, and radiant energy. And I'll give you just a couple of quick examples. So like chemical You could think of that as, for example, an internal combustion engine, an ICE, is going to take chemical energy stored in gas and it's going to turn it into the motion of the car. But in order to do that in between here, you need the internal combustion engine, right? Like you need a complex process, right? That I think most of you guys probably wouldn't even understand how that works at this point, and that's fine. We'll cover it later. But hopefully that's an example of I can get the chemical energy out of the gas to become the motion of the car, but I've got to go through a complex process to do it. It's not simple. It's not going to come out on its own easily. So hopefully that makes sense out of that. These other ones I'm not so concerned with you necessarily knowing all of them. It's just kind of extra information. So thermal energy, that's you have something that's hot and all the molecules are moving around. Chemical, like I said, something like gas, something like that. Nuclear is specifically when you have energy stored in nuclear bonds. So notice that's different from chemical bonds versus nuclear bonds. This is like the bonds of molecules. This is the bonds of the nucleus. And if you take Physics 2 next year, we'll talk about those a little more. And then radiant energy is energy carried by photons, which is just light. So, solar energy is one example of that. So going on to the equations, most of these are pretty straightforward, and we're going to shift our focus back to the mechanical energy. So again, if I kind of try to bring our attention back over here, right? If I take a look at what's going on with our taxonomy, the equations are really only concerned with these guys here. I really only care about those three. So if I look at those equations here, you'll see they're not very complicated. We just have to decode them a little bit. So it may be obvious, but this K here, that is kinetic energy, K for kinetic. And then the pieces that go into that are that you have a mass and you've got a velocity. So how fast the thing is moving and how large it is or how massive it is. Those are what matters for that. You may notice these two U's here. U is always going to be short for internal. And in this case, that means potential. So it's energy that's not motion, but could be. So that's our potential, G for gravitational, potential S for spring. And so these, again, I think they're pretty straightforward equations. You've got another M here for mass. G we should be familiar with being gravity. And then H, that is the height. That one can be sometimes a little tricky because really what I want you to focus on there is it's a relative height. Quick example. Let's say I'll draw a little doodle over here. Let's say I have a ball and I've got another ball, but that ball is over a table. So there's my crude drawing here. Well, I could say that both of these balls are, say, 2 meters high, but this table is a meter high. So if I look at this ball over here, it has more potential to fall because it could fall further. And so its relative height, what I would plug into the H there, that's going to be 2 meters because it could fall the full 2 meters. This ball over here, it can't fall the full 2 meters because there's a table in the way, right? So its potential for falling is less. So I wouldn't want to say that its height is 2 meters. I'd want to say it's 1 meter. It's the difference of these two. So one of the things we'll have to be careful about when we talk about potential energy is establishing a good kind of baseline for measurement. Last year, we've got the spring potential energy here. A couple things to unpack here that are a little funky. The first one is this K. We've seen that before, but we haven't used it a ton. That's the spring constant. So that's a measurement of how strong the spring is. It's got units of newtons per meter. We've talked about that before. Not a huge deal. Just if you see newtons per meter, you should be able to identify that as the strength of the spring. And then we've got this X here. That is the amount that it's been stretched or compressed. So if it's been, stretched 1 centimeter, that we would put that in there. But we want to put it in meters, so 0.01 meters. So that's that equation there. All of them, I think, are fairly straightforward. And let's look at some examples now. So energy examples. So this first example, we're just worried about identifying what's happening here. So I've described this as a mass that's oscillating. If you're not familiar with the term oscillating, that just means that it's moving back and forth in this case. So it's oscillating horizontally on a spring, keyword, and has reached the furthest point of its oscillation. And I want to know what kind of types of energy there are. So before we start unpacking this too much, little doodle. So this is like surface. I've got a spring, and I've got a mass. And the mass is doing this. It's going back and forth like this, right? And we're specifically trying to look at the point where it's at its furthest point. So that means that what I'm really looking at here, hold on, computer's being weird. What I'm really looking at here is when it's fully stretched out all the way over there. Now, before we dive into the energy part, let me tell you a few questions that you should ask yourself. So we've identified 3 different types of energy, and there's a question that goes along with each of those. And those questions are, number 1, is it moving? If it is, it's got kinetic energy. The second question we want to ask is it stretched? Is something stretched or compressed? If it is, then you've got potential spring. And the last one is, are we at some sort of relative height? If we are, then there's potential gravitational. So we should just be able to kind of look at those 3 questions and try and answer them and check them off. And then that's the kind of energy that we have. So if I'm looking for this one, let's start with the obvious. Is it stretched or compressed? Yeah, there's this spring here that is stretched as far as it goes. So I've got potential spring. That's an easy one. We can see there's no vertical motion, so there's no gravity. That one's out. And then last, we have to ask, is it moving? And here, the key that it's at the furthest point is going to be critical, because if it's at the furthest point, it's kind of, it's turning around, we could say. And if I'm turning around,